Hello, everybody. I will now present our paper, A Goal-Oriented Requirements Engineering Approach for IoT Applications. A requirement has been variously defined, and we adopt the definition as in IEEE. When this definition is applied into the IoT domain, a thing is the system component of interest. The condition or capability of a thing is that it may obtain data, optionally process this data, and communicate it to another thing. Now, this data may be obtained by sensing the environment or as a communication from another thing. Thus, we derive the definition of a requirement in the IoT domain as a statement about processing and communicating data. Now, let us consider how to represent an IoT requirement as a goal. Central to the notion of a goal is an objective, which in software engineering or information system indicates identification of a functionality. However, the mere fulfillment of the functionality is not enough in an IoT domain. In an IoT system, the objective is fully achieved only when communication is achieved. We define an IoT requirement as a goal of things, GOT, which is a pair, functional objective and communication objective, or in other words, FO, CO. For example, maintain life can be a goal for an Internet of Things, which can be represented in terms of the functional objective, estimate battery life, and a communication objective, inform battery status. Goal reduction can be done along FO and COs, thus building an and/or hierarchy. Can be actually represented in a model-driven manner, which we refer to as the GOT model. GOT is an aggregate which consists of exactly one FO and one CO, as indicated by the cardinality. CO internally is composed or is an aggregate of exactly one sender, one receiver, and one message. The sender may be physical, may be virtual, may be a cloud, or may be a user. The message can be sensed data or processed data which is obtained after removing false positives and false negatives. The model also proposes three types of GOTs. Simple GOTs, which cannot be decomposed any further. Complex GOTs, which are composed of simpler GOTs. And abstract GOTs are those that enter into generalization and specialization hierarchies. Notice that complex GOTs correspond to the AND of goal orientation and abstract GOTs correspond to OR of goal orientation. It can also be implied here that FO and COs may themselves be simple, complex, or abstract, and further the sender and receiver of CO may themselves be simple, complex, or abstract. Now let us look at the rules for interaction among the FO and CO. They are specified by 4 rules. The first rule considers complex sender or receiver. If the sender is complex, then only the complex sender sends out the message to the receiver. The components do not send out the message. Let us take an example where we consider a milk van which is composed of 3 regions. Each region senses its own temperature. The milk van is the sender, is the complex sender, which calculates the temperature, average temperature, which it sends out in terms of the average temperature. The next segment of the rule considers if the receiver is complex. In that case, all the component receivers get the message. So let us take the example of a complex receiver called operations having components cooling unit and recording unit. Now, the average temperature sent out by the milk van is actually received by the components recording unit and cooling unit. This can be seen in terms of our GOT representation of FO being calculate average temperature, the sender being the milk van which sends out the average temperature, and the receiver being the operations, and each component of the receiver, the cooling unit as well as the recording unit, receiving our average temperature recordings. Rule 2 considers the communication with abstract sender or receiver. Here the rule states that when the sender is specialized, then any one or more possibly all the specialized senders can send out a message. The receiver is specialized, then any one or more, possibly all the specialized receivers can receive the message. Again, let us take the example of our milkman, where we have a region, and let us consider that region to be specialized into back region and front region. Let us also say that our region has a cooling unit, and let's say that the cooling unit is specialized into a back cooling unit and a front cooling unit. Then one of the decompositions that we get is shown on the slide, where we can see that any one region is able to send out the message. Now let us shift our focus to FOs. Rule 3 states when the FO is complex, then only the data from the complex FO is available for communication, and all the component FO's data is subsumed by it. This case can be considered as compute average temperature. Any cleaned data is not available for communication, and the final average data computation is the only one that is available for communication. Rule 4 is when the FO is abstract and has specialized FOs. Here the data available from only one of the latter may participate in a COT. Now let us consider the requirements engineering process. The requirements engineering process considers how the hierarchy is built. The first step is formulate GOT, in which the GOT pair is completed. This is because it usually happens that either the FO or CO is elicited first. Therefore, it is necessary for us to formulate GOT in order to complete the GOT pair. Once this is done, the GOT reduction step can proceed. GOT reduction is done along 3 dimensions: the functional objective, the sender, and receiver. This gives us 3 drives: the FD drive, the SD drive, and the RD drive, respectively. In carrying out each of these drives, the next level of reduced FOs, senders, and receivers is determined, along with the nature of the FOs, senders, and receivers. That is, whether they are simple, complex, or abstract. We can go up to any level of depth in each of these drives. This is indicated by the self loop. Once we exit from each of these drives, we have to formulate GOT again. This is because we need the complete GOT pair. The process terminates when simple GOTs are reached and no further reduction is possible. We apply our GOT requirements engineering process to an accident example. Here the main requirement is to alert help providers in case of a motor car accident. Here thus we get the GOT accident alert as the FO and inform help providers as the CO. Since the sender and receiver in the CO is not fully articulated, we call upon the formulate GOT step and the full GOT is obtained. Further, after the full GOT is obtained, we send our GOT through the functional drive, the sender drive, and the receiver drive, and we obtain the following tables. The full case study can be obtained from the paper. We compare our proposal with one goal-oriented approach and one use case-driven approach. We found 3 major differences. One was ours is a model-driven approach. Therefore, identification of the functional objectives and communicational objectives is part of the model-driven approach itself, is part of the requirements engineering process. In the other cases, explicit domain modeling was required in order to discover the functional and the communicational objectives. The second difference we found was that in the notion of the message sender and receiver, there was no guidance that was given in the goal-oriented approach that we found, and in the case of the use case approach, these concepts did not exist. The third difference that we found was a full reduction that we were able to provide in our model was not there in the use case approach, and in the goal-oriented approach, the definedness of the technological goals was not really specified. In conclusion, we find that in an IoT application, the thing functionality and thing interaction form one integrated whole. We have defined a GOT that integrates the notions of functional and communication objectives. We further structure a GOT that permits specification of a variety of communication needs. Thank you.